we might as well do this. Okay, and then also quantum computing. So with that, I will get started. So it's going to be relatively short, but hopefully intense. I'm hoping that I am detecting the kind of content that would be interesting to you right. So my apologies if I missed the mark there, because I think we have a very varied set of attendees with a lot of different backgrounds. And so forgive me if that's the case, and please let's have in our Q&A items that we might want to talk about. So I start with, I will intersperse the talk with a bunch of quotes, which I like. Some of them are from us, some of them are from me, some of them are from a lot more famous people than us. So I start with the quote that you've all seen from Richard Feynman in 1981, but the physical world is quantum mechanical, and therefore the proper problem is the simulation of quantum physics. And we all know that that's what led or sparked the idea of building a quantum computer. Quantum computing are being used fundamentally as an accelerator to classical computing. So that leads us to try to categorize them in the way that you see on this slide. We have digital and classical on the left and top hand side, and then increasingly quantum and analog on the bottom and to the right. So when you look at digital and classical, we see clusters, traditional computing clusters that are common in cloud providers and supercomputers and such, GPUs for graphical processing units, and GPGPUs for general purpose graphical processing units, TPUs, FPGAs for field programmable gate arrays. So those all represent digital classical acceleration that we are using. Quantum basically takes it all to the bottom, away from classical computing. On the digital side, we've got the quantum gate projects that are going on. And on the analog side, you have the quantum annealing that are going on. On the top right-hand side, classical and analog is an emerging field that we are also trying to keep track of. In fact, the slide you're looking at is a collaboration that we've had with a very small startup out of Stanford called Radical Semiconductor that are working exactly on mixed signal semiconductors, where analog and digital capabilities come together to solve really difficult nonlinear problems that are not so efficient to solve with the clusters and are as yet not soluble with quantum computing. So that's one way of thinking, getting our bearings, so to say. This is kind of our one slide on what quantum computing is. The idea of quantum computing, we think, is everything is a probability function. It just so happens that it is possible to control it, and it's possible to use it and harness it. I think somebody put it well. I now forget who said it, but it was brilliant, that quantum computing is simultaneously overhyped and underestimated. It is hot. It will remain hot for at least the next decade, the way we look at it. As you know, the current state of the market is NISQ, for noisy intermediate scale quantum computing, because we are now past a couple of few qubits, but we are not yet to the levels that are necessary. There's a big global push towards quantum computing with tens, if not hundreds, of serious efforts in multiple applications in different geographies. It is fundamentally used as an accelerator, as we talked about, to classical computing, and the programmability of them is advancing. And the buzzwords of quantum computing that we often talk to our colleagues and clients is, one is that many people refer to it as quantum information science, so we need to be prepared to see QIS as a way that is referred to quantum computing and quantum communication and quantum sensing, etc. Quantum supremacy, and of course, Google had the tempting opportunity to wave the flag for that, and it did so last year. Y2Q was years to compute to quantum supremacy, quantum safe cryptography, and we're going to touch on that a little bit later on. QML for quantum machine learning, quantum error correction, quantum key distribution, and all these other kind of acronyms that we see that we want to be prepared for. So if on the left-hand side, you've got probability functions, what the industry is kind of addressing it with qubits, focused on decoherence. Oftentimes they need cryogenics to address that. There are many approaches, and it is hard to tell which one of them is going to win. Even in the solid state way, you got kind of silicon and photonics and trapped ions and trapped atoms and positronics and lasers and boson. So there's a plethora of approaches that are being out there trying, and it's kind of hard to tell right now which one is going to win. Many of them basically reduce to annealing and optimization, and all of this is towards the whole universal quantum computing that we all wish to exist sometime soon, but probably won't be anytime soon. The market segment. So quantum computing really started as quantum computing, but it has rapidly now segmented. So as of about like a couple of months ago, we are now formally segmenting it into quantum computing, quantum communications, and quantum sensing as three really separate markets. On the quantum computing side, it started with quantum annealing and D-Wave and some of the other similar efforts. We moved to the gate model. Some of the new approaches there with photonics and topological error corrections are looking really interesting. We talked about cryogenics that always or often seems to exist. Decoherence and quantum error correction are issues. And the metric that IBM first put forward, but I have no doubt somebody else would have if they didn't, because it just kind of makes sense at the moment, is qubit count, qubit speed, and qubit fidelity. And that is the envelope that they've been tracking in a good way. And I think it's kind of emerging as a standard also because a few other vendors have adopted it now. On the quantum communication side, which is what's related to the impact of quantum computing on blockchain, we look at entangled photons that are being transmitted. We're looking at quantum repeaters that take that transmission and basically replicate it and ship it and amplify it. There's a lot of work in teleportation, especially in China. And in fact, there are even talks of quantum internet, which probably is unlikely to replace internet as we know anytime soon, but it is able to actually send not just the keys to the packets, but the actual packets themselves. On a quantum sensing side, we've had examples in the old days like atomic clocks or magnetometers, but there are some emerging uses with sensors that respond to quantum stimuli, and you've got the quantum energy levels, and when they get perturbed, you can actually measure the energy level quite accurately. And what is new is that we are now moving to single atom level and using entanglement to improve accuracy and sensitivity. Was there a question? Happy to pause, but so please do so, because I can't really see who might have raised a hand or asked a question right now because I'm in full screen mode. All right, so here's a quick snapshot of quantum computing that as we see it. In terms of being overhyped and underestimated, we think that the vast majority of motivation to participate in this market is fear of missing out. Our joke is that for a market that really doesn't exist, there's a really big market that does exist, because everybody is in fact managing to get funded and people are raising really good levels and able to really push it. And I think at the government level and the large organizational level, it feels like a must-have or a must-be-present kind of technology. Nevertheless, it is a bit of a Wild West. There's a bunch of unpredictability, and we are now moving gradually from is it quantum computing or is it not, to what can it do and what are the applications. And as a result, the products are moving from science and engineering and computer science to actual productization. This has caused a lot of effort and focus on development software. It is invariably open source because everybody who's participating has seen that movie before, and they know that if you can have an open source model that can capture users, that's going to be advantageous in the market in a big way. They're all cloud-based. There are simulations and simulators that are on the cloud and try to make that a possible and a smooth curve. And we talked about annealing, gate model, photonics, topological as some of the products that are out there that are starting to provide some information on what they're good for and what they're not. And then the algorithms, obviously probability functions, because that's what it's all about. So if you have a problem that really requires probability functions, you might think that there's a good fit. And indeed there is. They have managed to do matrix algebra. It takes a long time to actually ingest the data and set up the qubits and get them all good and ready. But once you do that, you can actually do pretty large matrix algebra, and that is helping in some of the applications. They have been used for quantum sampling, for quantum classification, and of course, we're all familiar with Shor's and Grover's algorithms that are super speed up, and hopefully at some point we'll be able to use them in a better way. In terms of applications, all of that translates into what we consider to be 4 classes of applications for quantum computing. One is optimization, because that is all just kind of looking for the minima, and those probability functions can do that. Quantum science, so if it's quantum chemistry, it already should lend itself to quantum computing, except that it is such an early day for all of them. I've been attending some of the quantum chemistry talks that have been given on quantum computing for quantum chemistry, and it just feels such early days, really, really early days. Machine learning, likewise, it's a combination of optimization and matrix algebra. And of course, cryptography, a lot of it has to do with Shor's and Grover's algorithm. And if you can do prime factorization way faster in polynomial space than exponential space, then obviously you are way ahead. What is also interesting is that we now are seeing heuristics quantum-inspired algorithms. I didn't mean to make it quant-inspired. It's quantum-inspired algorithms. And that's led to the word dequantization, where you go down the path of quantum computing, you come up with an algorithm, and it turns out you can implement it on classical computers quite efficiently, so why not do that? And what is the actual use? Actually, when Google came up with their quantum supremacy and the random number generator that they had, we call this embarrassingly quantum. As a kind of in the supercomputing world, there's a label called embarrassingly parallel. And these are the applications that are so easily parallelizable that if you don't parallelize them with high efficiency, it should be embarrassing for whoever is doing the programming. So that also looked like an embarrassingly quantum application. And at the time, it looked like that maybe it was just going to be a toy or a kernel, except that it turns out provably random numbers, like we heard a couple of sessions ago in this meetup, is in fact really important. So provably random numbers, take that as a note, as an important application that is also happening. All right, so I'm going to now switch topics and go a little bit on supercomputing, and then AI, and then blockchain, and then talk a little bit about the impact of quantum computing on each one of them. And hopefully you find that interesting and not something that you already knew or were bored by. So this is a quote from us from many years ago, that if you have 200 rows in your spreadsheet, it's a spreadsheet. But if you have 2 billion rows, it's supercomputing. So what is supercomputing? Supercomputing is fundamentally about everything is computable. You name it, I can compute it. Maybe not now, but I will do it later. So it has to do with digitization. It has to do with the generation of the data, the application of science, technology, engineering, mathematics, plus information technology to get to high performance computing or supercomputing. Now, because the applications of supercomputing have initially been in science and in engineering, they also had to start with that. So, you're going to have to go back to Galileo and the scientific method, and you say, I have an experiment and I got a new idea, and or I have a new idea and I do an experiment. So that gives me a theory, and then computing became a third arm of that by having simulations. So experiment, theory, simulation is what science has been doing for about, I would say, 40, 50 years, maybe even more than that. So now that you're simulating, you may just find a new way. So now you can automate it. Once you automate it, you can instrument it. When you instrument it, you get new data. When you get new data, you need to make sense of it through visualization or AI, and that leads you to new simulations, and you've got communication in the middle. So fundamentally, we look at supercomputing as these 5 modes of computation: simulation, automation, instrumentation, visualization, and communication. When they come together, they really become the kind of human scale advance and grand challenge solutions that we see. And that's why supercomputing has always been a good beacon of where science and technology is going. Now, AI is really an application of supercomputing to what used to be artificial intelligence with heuristics and expert systems and such. So we think if HPC is about everything is computable, AI is about intelligence is computable. Aha, so this is the first time that we are actually trying to encroach on humans' monopoly on intelligence. And we're not there yet, but it's kind of a set that gradually expands. So AI is also quite strongly related to IoT because that's the fountain of data. Now, once you have fountain of data, you need to apply the big rules of big data. So because data can be dangerous, as we are observing even these days. When you look at data that is incomplete, it's irrelevant, it's irreproducible, it's just kind of not doing what it's supposed to do. So bad data is worse than a bad opinion. So one, we have to be really careful about the data. But once you have that, you can apply AI to it. And the way we have categorized AI is in this picture, as you see, with AI at the bottom, big data at the bottom, big data at the bottom, AI at the top. As big data comes up, you can look at it on the left-hand side with simulation and HPC, on the right-hand side with automation and IoT. There's a lot of AI that is simply sophisticated automation. And there's a lot of AI that is actually understanding what the semantic meaning of it is. And it is a lot more deeper in terms of the computational aspect. So we essentially think it comes down to numerical models and logical models, with numerical models being statistical and optimization oriented, and the logical models search and expert system oriented. And ultimately, the real AI is going to have a combination of all of them. So the next quote is from a paper we wrote back in 2016 on artificial intelligence and the grand challenges of artificial intelligence. And this continues to be really quite valid, that no different than industrial machines, information machines can help, but only when the scope of their activity is fully defined. If it can be defined, it can be automated eventually. But whether or not and how well it can be defined is really the crux of the matter. Now, we looked at Asimov's 3 laws of robotics and how it needs to be proper and not do bad and all that stuff. And we think that needs to get successfully programmed into our AI. So what are those grand challenges? It is unpredictability. It is unintended consequences of AI. It's a system complexity that can exceed human competence. It's the ethical complexity. Is it used for good or is it used for evil? Is it for elimination of large classes of jobs by AI is already a problem? Is it a Darwinian mistake to make it happen? And the Asimov rules that we talked about. The legal framework is arguably more important parameter than technological advances. And then we all talked about autonomous systems and autonomy, but autonomy is going to be limited by the precise definition of the scope. Just like you can't use like an earth mover to, on a race car because it's kind of being used outside of its scope. We can see how even like driverless cars, when they see a situation they've never seen before, they can't operate. And, and that leads to what is our tolerance for mistakes when a machine makes the mistake? And what level of expertise do we need a machine before we can let it replace human beings, or specifically one particular human being? Okay, so now the impact of quantum on AI is that obviously it's an accelerator that is attached to supercomputers. It can do matrix algebra. It can do optimization. That means deep learning can now be used, and it is being used in some of those applications because we can do matrix algebra. Much of AI is finding a minima on a hard and complicated surface that feels like optimization and probability functions, and it does that in a good way. But then really a lot of the recent advances on quantum-inspired and digital annealers and analog accelerators, where quantum is really being a catalyst rather than the end solution. However, of course, it's early days, and as time goes by, we'll see how it works. All right, next one is blockchain, and hopefully you're keeping up with me and you're fine with the way this is going. Blockchain, this is also one of our quotes. For those of you who are old enough to know who Ingmar Bergman is, you know what I mean. Blockchain is like a Bergman movie. You know it's important, but you don't get it. And anybody who's been in a Bergman movie knows exactly what I'm talking about. But John Oliver, who we all know and like, also had a really funny thing to say. It's that it's everything you don't understand about money combined with everything you don't understand about computers, which also is rather true. So we're going to do a really quick course on blockchain and cryptocurrencies, and we take it from there. Is it digital money? Well, it's the beginning of digital money. So the 3 columns here that you see are what I'm going to recommend that you do. One is that if you haven't already looked at blockchain and cryptocurrency, the place you want to start with the original paper, the so-called Satoshi paper that was published in October of 2008. In fact, it was published just about the last time we had an economic meltdown. And in some ways, it was a response to the economic meltdown, or at least that's the story that is being told now. But it's an incredibly accessible paper. It is the authoritative one. you're going exactly to the source, and I highly recommend that you just take a look at even the first couple of pages of it. If you just get on Google and say Satoshi paper, it shows up. It's all over the place. But it is peer-to-peer, it's electronic cash, it's tried to solve the double spending problem, it uses hashing, it uses something called proof of work, which is hard to understand, but it's basically a lot of energy to spend to prove that your intentions are proper. And if you do it, you get rewarded, and if you don't do it, you basically get penalized for having wasted that energy. The components of this digital money are coins or tokens. They're addresses that are essentially referring to where those coins or tokens belong. It's cryptography. It's wallets that keep track of where these things are. They're smart contracts, exchanges, and apps, all on sort of a general ledger. The Bitcoin, as a prime example, and continues to be probably the most trusted coin out there, it's essentially digitized gold, complete with the mining analogy. And with big blockchain being just a distributed ledger where authenticity is assured through computational challenge. And it is increasingly accepted. There are increasing use cases, but there continue to be legal challenges. So what is it? It's the digital money. So digital money wants to be a store of value. That means, is it safe? Can I store it there? It's a unit of, please.
I just wanted to, if you could go back to your previous slide, I just wanted to point out something about the research paper. I'm really glad you brought it out and mentioned this timing of the financial crisis. So in the chat box, I just posted up actually in another original paper that was written in 1996 by 3 or 4 engineers and mathematicians and cryptographers by the NSA. And you might be familiar that SHA, SHA, the 256 as well as the 200 series was developed in, I believe, in the 80s by the NSA. So there's quite a bit of interesting ties to this. And, you know, if you're into research papers, this is definitely one you want to read from 1996.
Yes.
And you'll see a lot of correlation. So in terms of like timing, it was definitely well-timed and well-planned, but that's all I'd like to say.
Well said, well said. And in fact, as you just mentioned, the history of digital money goes way back to October 08. It is far from the fact that Satoshi just kind of started it. There have been a lot of talks and proposals and theories, and it was building, and several people had talked about it, and different components of it were coming together. What is really interesting about the Satoshi paper and Bitcoin is that it is really a Goldilocks thing. It is like a half a dozen things coming together just so. And if you mess with one of them, the whole thing falls apart. And it's not like it hasn't been tried. People have tried to reformulate it this way or that way. And there are other coins that are doing very well, but every one of them makes a compromise. And I believe that, in fact, one of the things that we're going to see in terms of digital money, our thesis really, as an analyst firm, is that digital money is about disaggregation of the dozen or so attributes of physical money, cash, and then reaggregation of it for specific use cases where you let go of some of the attributes and you preserve some other attributes. And I think that's kind of a fair way of analyzing. But yes, for those of you who are interested, the paper that you just put up is awesome, and it's and you will see many more as you study it. Very well, thank you. And please, others, if you'd like to make a comment, please just kind of somehow make your presence known, and we'll have a conversation. All right, so it needs to be a unit of account, and a unit of account goes straight to what is the supply of money. Money supply is a really big deal for those of us who keep track of the global economy and what the Fed has to do, and now is doing even in more visible and previously unexpected ways. They're now actually going to buy corporate bonds. They never did that. So it's like, you know, quantum easing to the max, you know, part 4 or something. So all of that is really showing the difficulty of managing money and money supply in the world of fiat, just kind of physical currency, government issued currency, and how it is changing in the digital world depending on what coin you're talking about. It needs to be a medium of exchange, and that requires stability. And of course, there's way too much randomness and volatility in digital coins right now for them to really be a medium of exchange. So the wheel that you see is some of the aspects of it. It's all digital, it is decentralized, it is consensus-based. The consensus algorithms are proof of something, proof of work, proof of stake, proof of something, or they are like directed acyclic graphs that are another way of approaching that sort of validity. Byzantine fault tolerance, that all sorts of algorithms go in there. It is open source, very, very important piece of it. And fundamentally, it's an immutable ledger. Now, immutability goes smack against data privacy. I mean, by definition, if you participate in a blockchain like a Bitcoin, there's no way you're going to erase your footprints. It's immutable. You signed up or initially. But cryptographic and the keys and the identity and the hashing functions that are very much part of this thing are really where quantum computing can have an application. So let's look at public key encryption. So the basic concepts on the left-hand side is like the old ways. This is symmetric key encryption. Both sides need the same key. So that means you and I, if we want to communicate, we have to have the shared secret key. Well, if you haven't met to kind of do that, if you have to communicate through a third party, it's really difficult to avoid eavesdroppers. And for those of you who read Roman history, you know what all that meant. If you got eavesdropped, bad things could have happened to you or to some other people. So you'd need a trusted way to communicate. And if you don't have it, all bets are off. And of course, on the internet, you're not going to have it. So this led to the middle one, which is asymmetric public key encryption. So now you have to assume that eavesdroppers are out there, but it is impossible for them to decipher what you're talking about. In order to do that, you need three ingredients, such that you need a function with three ingredients, such that function of a comma b comma c is the same as function of a comma c comma b. So there's some commutative property there. Now, the important thing is that f is really easy to calculate, but its inverse is really hard to calculate. And that's why it's called asymmetric. For example, modular arithmetic is like that, right? You can say something modulo something, boom, you know exactly what the answer is. But if you go the opposite, you have no idea because there are like millions of choices. So in this case, A becomes public while B and C are private. A very good analogy is mixing paint. If you and I both have our own secret paint colors and we agree what a shared public third paint is, that would be kind of A is public. Now I can get that public paint, mix it with mine, and nobody knows how I got to that mixture, and send it to you in a public way. And you do the same, and then I get yours and add it to mine, and you get mine and add it to yours, and we both end up with the same paint. And now we both have the same ship of paint, and then we can now encrypt all to our heart's content because we just moved it right back to the left column. We now both have the same shared key. Now, this is one way of doing it. There are half a dozen other ways of doing it that make it a little bit easier. And you have to kind of trust that that happens unless you're going to study this for detail. Now, in the quantum world, you do need provably random numbers, as our speaker a couple of times ago mentioned. That's an important piece. But fundamentally, it's quantum key distribution. So you send the data in normal ways, normal encrypted ways, not quantum safe ways. But you get the key and you send the key in a quantum way. Now that's basically an entangled key transmission. So you send the keys in an entangled way. If anybody tampers with it, it all collapses. And when you get it at the other end, you kind of do some level of testing. That's called kind of sifting and distilling. And you distill it and you decide both of you decide whether what you got is trustable or not. And if it isn't, you just do it again. And then you do it again until you build confidence. But once you have the key, you can now go and decipher it, and your key was safe. All right. We're going to come back to that. Okay, that was the paint chip. I can move forward. This is the hashing. So the other piece of cryptocurrency and blockchain is trust. And it is decentralized trust, or some of them call it zero trust. And the important thing to know is that trust is expensive, as we said also in one of our quotes. And really corollary to that is that if you have trust anywhere in your life, cherish it because it really is expensive. And these are basically the two choices. If you want trust, you either get it through faith, fees, and fiat. You have to have faith in some authority that's going to be trustworthy. You have to pay fees to keep that authority in business. And you have to deal with the fiat and the dictation of that authority because that's how they have to do that. And our interaction with a lot of different pieces are like that, and it's okay. That's not a problem. It's not a problem in many, but occasionally it can be a problem. On the right-hand side, you need to have presence, you need to have participation, and you need to have electrical power. None of these cryptocurrencies work if not enough people are participating. None of them work if they're not applicable to what it is that you're trying to do. And none of them work if you don't have enough compute power to make sure honest people are kept honest and the bad guys are penalized for having wasted all that money on computing where they could have become good guys and actually got rewarded for that. All right, so essentially we're saying trust is now computable too. So everything is computable, it's all probability functions, intelligence is computable, and now trust is computable too. So this is how computing starts encroaching on human beings. So this is the emerging stack. I'm not going to go through it in detail unless there is really a desire to do so. But if you look at way at the bottom of that slide, you see we have monolithic applications to multi-tier applications, to scale-out applications, to elastic applications, to serverless applications, and now to decentralized applications, which can be a permutation of some of the ones before, but they are using the stack from the left-hand side to the right-hand side. Now, we think that blockchain can be used, or it's kind of eligible to be used, when you have natural scale, when you are naturally distributed, and you can assure a certain level of participation. Now, on top of that, if you want traceability of something, or if you have some smart contracts that can govern things, or if you need to make sure authorization and rights management is an issue, then you've got the ingredients necessary to use blockchain. If you don't have those, traditional ways of doing it are probably better, faster, cheaper, and you can find developers who know how to do it. All right, and now we go to the next one. Now this is smart contracts. Smart contracts are essentially code. You have open source, they're stored in the chain, they're event triggered, and they're on-chain, off-chain transactions. So smart contracts can really disrupt legal contracts. However, they must be precise. The translation from natural language to legal contracts is really difficult. That's why we hire lawyers. All legal contracts are essentially code. And if you've read more than a half a dozen, you know just how bad a code they are. They are terrible as code, at least the ones I've been reading. Some of them are beautiful. Some of them you read and you say, God, that really is so airtight. But we have seen lawsuits won and lost on the interpretation of one word or one punctuation mark, right? Just look at our Second Amendment, right? Just that little comma can cause big, big problems because it wasn't written clearly. So it must be deterministic. That means code verification, language level enforcement, state machine. All languages claim to be Turing complete because they think it's a feature, but in fact it's a bug. Turing complete means there's no way I can verify it at the moment. So all of that is coming, and it is like really interesting. And it must be secure, it must be immutable once it's on the chain. And a lot of people are working on these things that we need to recognize. Okay, so I'm starting to get to the end of the conversation on the slide deck. This is our view of the future. The future is IoT, blockchain, quantum, AI, where machines, bots, DAO stands for decentralized autonomous organizations, and dApps for decentralized applications are doing most of the creating, consuming, and paying. So it is important to note that a lot of what we're talking about is not even for human consumption. Essentially, humans are standing on the side of a giant digital pool with a toe in there. And occasionally there will be a transaction that tickles our toe. But most of the action is going to be in the pool among all these digital entities that are doing it on our behalf and for each other. And I think if you think of it that way, suddenly some of these technologies become a little bit easier to understand why you don't find them useful, because, well, guess what? They're not for us. All right, so that's the end. I thank you, and see if we can go to if there are any questions. Now, if I'm not mistaken, you're all unmuted, but I'm going to make sure that you are. Okay, so you can all unmute yourself at this point if you'd like.
So I do have a question for you,
Please.
hypothetical. You know, if we look at Moore's law and the evolving computation, and we look at some of the older technologies of hashing mechanisms like SHA-256, and as robust as, you know, these validation checks between all the nodes verifying that this transaction has per se happened, do you think it would be possible to, you know, the question is like, can the emergence of quantum computing and the right algorithms disrupt some of these older blockchain technologies?
It's possible, and you know, we as an analyst firm really like proof of work as the safest, most secure way of having a consensus algorithm. Many of the proofs of stake or DAGs or others are exposed in some fashion. There are some new technologies that look more promising. There's at least a couple of coins that are already quantum safe in terms of their cryptography or attempt to do that. So I think there will be an evolution. One of the nice things about Bitcoin is that you can fork the coin, and that can equivalent of a dividend if you'd like to just immediately sell it and move off. But it can also change the algorithms and such. So I believe that's what it's going to be. Should I quote everyone, and then you guys unmute yourself if you'd like to talk?
So I didn't get the last bit of what you were saying.
Right. I was saying that when one of the nice things about these chains is that they can fork. For example, Bitcoin has forked a few times, and sometimes with coins that are still around and, you know, paradoxically doing well. So some people took those as dividends. They said, aha, it forked, I can immediately sell it, I get some sort of a dividend, and I carry on with the main chain as it exists. But down the line, you can also see that if the chain itself doesn't become quantum safe in some orderly manner, you can fork it in a way that it is. And then the transactions would switch over to that fork. I believe that's how it's going to turn out. Am I answering your question?
I understand forking. I'm just talking about, you know, like, let's say I want to write a brute force algorithm that could somehow dislodge the blockchain that is built off of really hashing mechanism that goes back to the mid 80s.
Ah, I see. Can I do that? Well, I think what you're raising is, I interpret it in two ways. One is that it has been reported. I mean, one is about just blockchain itself, and can you go all the way back and rewrite history? It is increasingly a daunting task to do, and the algorithms to do it are going to be difficult to do. So it is highly unlikely. But you can say, well, I don't have to go all the way back to, you know, mid 2000s, or why not just go a month back? Can I do a month back? Can I do 2 hours back? Can I do 3 hours back? And as you move that time frame forward, it becomes more and more possible. Now, if you're like a nation state, if you have the wherewithal to really go and just attack it, you probably can. I think the system with Bitcoin, the way it is designed, is that if you took all that effort and applied it to just validating new transactions, you're likely to make a lot more money than what you could have done by trying to undo a transaction. So it needs to be just so. It needs to be like some big movement happens and you say, aha, that's my opportunity to get in and try to rewind the clock 15 minutes and see if I can undo it. Now, if you are doing that kind of a transaction, the more time that passes, the more secure that transaction is. So it's all probability, because the likelihood of exposure is not zero, but it is close to zero. So hopefully that answers that aspect of it, or at least is along those lines. The second way I read your question is, it's been reported, and I brought it up in our last meetup, that the bad guys are already recording encrypted data on the hopes that someday they can decrypt it with these new technologies. Now, by then, maybe the data is 20 years old, but you may still find some gems in it. You may still find some bits in there that are valuable for a bad guy. And I don't, and I've raised this question with a lot of others in the business, and really nobody seems to have an answer for that. If a bad guy is sitting on data that's already encrypted, well, you just hope that you catch them before they find a tool to decrypt it. Yeah, was this a little bit closer to what you were addressing?
Yep, a little bit.
All right, thank you. Right. Any other question or comment? Was this any good?
Yes, it was.
All right. Oh, somebody, Igor, you are able to talk, so please do. Oh, and we also have a couple of, go ahead, please.
Thank you, that was a great talk. Just have a quick question for you. So you talked about quantum computing and how it's going to be eventually made accessible through kind of an open source model. I wonder if what you said about quantum key distribution would also be made available. So for example, right now, or maybe in the near future, how can individuals or maybe small businesses, large businesses, utilize this technology, right? So right now, if I want to communicate with another person, I'm sending them public keys essentially.
Yes.
So at what point are you seeing a drive to make these services available to maybe large enterprises, small businesses, and eventually public?
Well, that's presumably already out there. There's a company called Quantum Exchange, whose name kind of comes up. And presumably they're working with the financial institutions, and there's already like a 500-mile radius that they've managed to incorporate in their technology. And it is used between Manhattan and New Jersey, where a lot of financial folks have their data centers. And they're already using quantum key distribution in that area. There's also talk of similar technologies in China. There's talk of a system that is in existence between Shanghai and Vienna, if I'm not mistaken. So they are going in that distance, including quantum repeaters, to make that happen. So there is a lot of effort with serious money behind it to make this happen. And of course it makes sense, because if you're sitting on that kind of a data, really the ROI of spending another $100 million to get this working becomes rather doable. So that's the way, that's the information that we have. And that does not include all the classical stuff. One of the main proponents of quantum communication is actually organizations like, Army Research Lab or other parts of the military. And that's not just in the US, also in other countries. And God knows what they're doing and for what reason, but one has to assume that it's real enough for them to put effort behind it. There's another question online from Dr. Law, thank you. It says, Shahin, do you see that we all own a quantum computer or accelerator in the future to be able to engage with the transactions applications described, or we need to all have access to a quantum accelerator? Well, I think the way this is working right now, given the dollar figures that are necessary, I see cloud providers recognizing that increasingly their differentiation is in the system configuration that they offer, not just the access and the programmability that they offer. So see Microsoft having different supercomputers. They have a Cray supercomputer that they offer on Azure, and they've got a couple of quantum computers that they offer, and they've got a simulator. IBM's IBM Q has been available on the cloud for probably more than a year, if I'm not mistaken. And others, Rigetti has theirs, and others, IonQ, I think was talking about it. QC Wave was a speaker a couple of times ago, and they've got a good development environment. So there's a lot that is a D-Wave, theirs is on GitHub, and we can go sign up and play. And if you sign up, they'll give you like 1 second of actual time on their machine, which is quite a lot of computation given how fast these things are. And you can probably get more if you show some interest, because they are trying to cultivate this sort of a thing. So I think cloud is the way to go. I think cloud is how you're going to get access, unless you're a Google or a NASA or a classified agency with the wherewithal to go buy your own, and you know why you're buying your own. Volkswagen presumably has one, Toyota presumably has one. And those are just the D waves. I don't know about the others. All right. Are we good? Is this it?
Question.
Yes, please.
Okay, can you explain a little bit more about the trust computing?
Right. So the question is, can you talk about trust computing? So the cryptocurrency blockchain is fundamentally based on a decentralized, distributed way of validating transactions. So instead of, if you're doing a financial transaction, instead of having to go to the bank to say, okay, you've got the money, okay, you're going to receive it, I'm going to take the money from you and give it to you, and they basically become the custodial, the fiduciary, the authority that can facilitate that transaction. In the cryptocurrency world, there is no central authority, so you have to do it in a decentralized way. So the trust that that central authority was bringing has to be replicated in a decentralized way by all the players in the network. So if you are a Bitcoin node, you can come into the network, you can leave, you can come back. But if you decide to participate in validation of transactions, you basically everybody downloads the same code. And if you mess with that code, then you're going to be kind of the odd man out, and it's not going to really work for you. But if everybody's running the same code and everybody's looking at every transaction, and everybody who is participating to be a block producer or to be a miner actually has a record of all the transactions and the entire ledger. So it is a distributed ledger. In the world of databases, this is way more than sharding. This is entire replication of the database on many, many, many nodes. So if you have thousands of nodes, each of them have a full account of all the transactions, then you can make it a little bit more democratic. So they can all vote. They can all say, these are the transactions. This is the record. This is the legitimate record. And in fact, in the Bitcoin world, if you read the paper, and I recommend that you do it, the longest chain wins. The longest chain is the chain. And the longest chain represents the largest amount of compute power that was put towards validating those transactions. So they do reward compute power, but it's on the assumption that if you do that, then you get rewarded because you mine coins, and every 10 minutes, another 12.5 coins are produced. Now, sometime in June, it's going to get halved again, and that's going to be a really big deal as the whole system transitions from what the miners get to what the transaction fees are. But the system is really incredible in the way that all of these different pieces come together. Now, that's just Bitcoin. If you look at EOS, or if you look at, Cardano, if you look at, IOTA, those are all different consensus algorithms, and they also have different number of participation. So there are some coins that are running on 2 nodes in somebody's lab with 5 people participating. Okay, that's pretty centralized, even though the application in principle can be decentralized. I hope I answered your question.
Yes, thank you.
So can we roll back the transaction if something goes wrong during the transaction?
Nope, it is immutable. So the longest chain wins. Now, if you submit a transaction,
okay,
these block producers have to select your transaction and put it into their block and hope that their block is the one that wins. So why should they use your transaction? Well, they can because it's just there and there's nothing else. But if there's a competition for transactions, they're going to select the ones that have a higher transaction fee for them. So it is possible to see that you submit a transaction, and if you want it to go faster, you may have to dial up the transaction fee that you're willing to pay. And the system gives you a bit of advice on what that should be. but that's how transaction fees might increase. But once the transaction is submitted in a block, if that block wins and it becomes the approved block, and the miner for that block reaps their benefits, and it gets into the chain, that's it. There's no going back.
Okay.
Okay, there's also a question from Helen. I'm involved with companies developing quantum-resistant blockchain. They're using the Lithium software and are confident that they are developing quantum-resistant frameworks. Any comments? You know, I'm afraid not. I have heard of the Lithium, but I have not studied it. So this is a good prod for me to go do that. I have no doubt, because as I was saying, there are a lot of very smart people working on a lot of different parts of this. And even though it is the early days, it is unmistakable that this is a new tool in the tool chest, and people are going to use it for the applications where it's needed. Getting it right is hard, but somebody's going to get it right. So maybe these guys have found it. We can go offline after I have a chance to look at it, and maybe also talk to some of my colleagues.
Okay.
All right. If you're in the mood to have a chat, you are going to have to unmute yourselves. Dr. Ghoshal, is that our cue that we have concluded?
No, you can do that, but you are going to send me the link, right? For the
Indeed.
slides?
Absolutely, I will.
Okay. Okay,
Thank you very much for the presentation.
Thank you very much. Really a pleasure.
Thank you. Thank you all for coming. We'll have our next month's meetup. You can see the website for this. You know, we may have 2 meetups coming up. Just check the website, okay? Thank you all. And
Very
thank
well.
you, Mr. Sain. Hope you're coming again to talk about more.
I
okay?
look forward to it. Thank you for holding these. Thank you all. Please stay safe, stay put, and have the craziness behind us soon. Thank you so much.
Thanks.
Thank you, Shahin.
Pleasure. Thank you.